Hi, welcome to Dunwoody Mechanical Engineering MENG3250. It's heat transfer. We'll be working through problem 542 from Bergman, Fundamentals of Heat Transfer. We'll be switching over here to my screen so you can take a look and follow along. We'll be using interactive heat transfer as we go through this. So I've got interactive heat transfer open. I've already toggled between the advanced and the basic screen, so you can already see up here I've got the basic is the option I've got available to me. If I flop that over, I don't want to leave my pen. So if you open it by default, you're probably in the basic. I'm going to switch over to the advanced. And this problem in particular, we've got a plate that we know some things about. So looking at our problem statement from the book, we have this plate that's 25 millimeters thick, comes out of our process at 600 degrees C, and we need to cool it down, and we're wondering whether or not we should cool it on both sides or just on one side using a stream of air that is available to us. So we're going to compare those two and see what we've got. We know the temperature of the air, the convection coefficient, the properties of the material, and we can go from there. So I'm going to go into IHT here, and I'm going to go into Models, Transient Conduction for a plain wall. Open that sucker up. And as we talked about in class the other day, we've got some descriptions here. So what are we assuming here? We're going to do a thickness of 2L. So the whole thing, and it looks like we're cooling on both sides. So we'll have to think back to our earlier discussions. I don't think I can ink on top of this, but if we think about that, we decided that if the cooling is truly symmetric, right in the center, we're going to have no heat transfer from the right to the left. So in that case, when we have the single side, we're just going to double the L value to get that full thickness, if you will, and cooling only on one side because it's like it's insulated right there in the middle. So we're going to double that L to kind of trick it into thinking it's only cooled on one side. So I'm going to grab these properties or the comments here. So we're going to model wall thickness of 2L, uniform temperature, subjected to convection. Perfect, that's what we've got. We're looking for the temperature at some position, and then we're going to make these assumptions that we have one-dimensional conduction X, uniform initial temperature, constant properties, and negligible radiation. Sounds good. So I'll drop those in here. Next, I'm going to go over here to my assigned variables. So this is where we'll put in our parameters that we need for the problem. We'll read about them in just a moment. So I'm going to grab those, drop those in. So our initial temperature, this is in Kelvin, so I'm just going to type 273.15 plus, our initial temperature was actually 600 C, so we can do that math right for us there. The half thickness in meters is 0.025 divided by 2. Our density is 3,000, that was given to us in the problem. CP 750 joule per kilogram Kelvin, yes. K is 15 watts per meter Kelvin. And our surface area, we'll just call it 1. We're not told how big this is, we're only looking for it on that. We're not looking for Q per se, we're looking for time to cool. Where are we looking for? We're looking for the surface temperature, or the center temperature, so I'm going to call X is 0. And time, we're going to run it up to 500. We can adjust that in our other bit here. And our convection, oh, I must have dropped, did I lose it? It shrunk this box on me. There we go. I was missing the T infinity, so let me add that in here. So my convection is 400 watts per meter squared Kelvin, and my T infinity is 25 C, so I have to add 0.15 for my conversion to Kelvin, and then my equations. So we're going to pull this in. We have functions as of our position, X star, it's that dimensionless ratio, our Fourier number, our BO number, our initial temperature, and T infinity. And this comes from equation 542. We're not going to worry about heat flux. We've got that there, but we'll grab it and then delete it out of there to avoid doing it in 2 steps. So I don't care about this middle section for this problem. And then we've got this bit here. So we should be able to solve this for the initial plate cooling on both sides. So let's solve that thing. So after 500 seconds, what's our final temperature? Tx star, we're at 299.2, which sounds pretty darn close to that room temperature air, so we're already cooled down. I could also hit the explore button here, which I'll do. So I'm going to go through time, and I'm going to start at 0, I'm going to go to 500, and I'll go by 1 second. Sounds like a little overkill, but it'll calculate pretty quickly. Ask me what I want to do with my previous data, get rid of it, and we're done. So now I can add a graph. So look at time versus that center temperature, and just as we suspected, it cools off pretty quickly. And actually in those later seconds, we almost have no cooling going on. It's reached close to steady state at that point. So that's the cooling on both sides condition. So you may be asking yourself, oh, how do I do the cooling on one side? Well, I'm going to grab some of these values here. So I'm going to double up this one. Oh, I don't want the whole thing, I just want the L. I'm going to call this L sub B, or just LB. And I'm going to double that, so I'm going to get rid of the divide by 2. And I probably need some other things in here. H, X is still that. Alright, so down here I'm going to need some of these other variables. So I'm going to call this, let's see, dimensionless variables. I'm going to call this X star B, BOB. I'm going to divide by LB, LB, FOB is alpha times T, is LB squared, alpha, K, rho CP. That's all the same material properties, so I don't have any L variability there. And I think that should do it for me. So I'm going to copy this temperature as well. So I want to calculate that for temperature B, plane wall. It's going to be X star B, Fourier B, BIB, T infinity and T initial are the same. And so now we should be able to get this on the same redefinition of a constant variable. Where did I redefine? Oh, I need to get rid of this guy because that was not named. There we go. What else did I redefine? Alpha, Fourier B, X star B, TX, X star B, Fourier. Where am I pulling that problem from? LB, XTH, H. I thought that should work for me. No. Well, what did I do to it? Line 44. Well, maybe it's not telling me where I'm doing that, is it? Redefinition of a constant variable. LB squared, LB, LB, TXTB, TXT, X star B, Fourier B, BOB, T initial, T infinity is that. Did I lose H? Oh, I defined T infinity twice. Let me get rid of that guy. I accidentally copied it an extra time. And I can get rid of this guy. I already had him there. Alright, I think I've got it now. There we go. So we'll get rid of that. Let's do an explore again. Going 0 to 500. Get rid of that set. Now we can do a graph. So we'll do our original. It's on one set, and then on the red line, I'm going to do the single line. I'll just add a note here, double cooling there, single cooling here. It's time. X-axis is time. Y-axis is temperature. Kelvin. Alright, so that's what we see. And as you'd expect, double cooling, we get cooled off much faster than if we only cool one side. We were asked specifically for the time to reach 100 degrees C, so I can use this Explore tool to do that. So, going pretty slow here. Let's see, so I'm 100 C, should be about 373, so somewhere around here. Usually that lets you do that. Can I click there? There we go. So I'm looking for 370, just randomly clicking. Okay, I'm getting close. So maybe we need to go a little farther. So between 164 seconds, I see that here, and 165. So I'm a little under 100 there. So around 163 to 164 for the double cooling. If I go on the other one, I'm looking for 373 here. It's a little high. So there I am at about 367. Gets me the temperature for, or the time to that 100 degree temperature, 100 degree C temperature for the single-sided. So there's a big difference in time from about 164 to 367. So what is that, about 3.5 minutes or so, give or take. So there's that output, and you could copy and paste this, you could print it, you could copy it, etc., and put that into your homework. I do want to close that window. Now the other thing we were asked for in part B, we're looking for maximum temperature versus the minimum temperature, the biggest temperature difference in the material. So I'm going to add another line to this, TXTS, and I'm just going to copy that same thing here. And what am I going to fill in on this guy? Well, I had X star before. Well, now I'm going to 1, right? So I'm going all the way to the surface. X is 1 over L. So we're going to be set there, and then I'm going to copy this guy here. I'm going to do the same thing, only I'm going to call it XTSB. Oh, I lost my mouse for a minute. Let's see if I can get that back. There we are. S. And I'm going to put that to 1 there. And now we can explore that, do the same darn thing. And now when I explore or plot these variables, I'm going to grab, I forgot one other piece. Yes, I want to close that graph window. I want to define a new temperature. So I'm just going to call this delta T equals T xt minus T xts. And down here, I'm going to call it delta TB equals T xtb minus T xtbs. And now we can plot those. Oh, I probably need to solve it again. So it hasn't defined what those are. Yes, I want to get rid of that. Explore number of unknowns. Delta xts, delta t, delta t xt minus t. Oh, missing the underscore. T. There we are. Now that should take care of us. There we go. There we go. So now we can plot that. So I'm going to plot delta T on one and delta TB on the other. So T is double-sided cooling, TB is single-sided. And as you would expect, single-sided, I have a much higher difference in those temperatures, which could lead to some thermal stress as a result. And it remains high for longer. And with the other, so I'm about, what is that, 135, give or take? 133.7, and on the other one I'm at a peak of 77.6. So as I look at that, it seems this double-sided cooling is a better approach if I have to cool this quickly. If I can just leave it sit and not worry about internal temperature gradients, maybe I do something else and just let it cool down naturally. So that takes us through our solution there. So what would I like to see in your homework? I'd like to see your model, so upload that. It's pretty easy to use the advanced features here in IHT. You do need to think about what you're doing, right? So when x is 0, that's our center line. When x is 1, or x is L, that's our surface temperature. I kind of manually made it go to the surface temperature down here rather than defining a new x for each of those. And we can plot those once we've done that explore function. So I hope that was helpful to you, and I'll see you in class.